question 3, the parity bit. Parity bit. We are having an even parity. We agree to have even parity here. So we can have odd parity, but now we are discussing about this even parity. Once you know how to do it, all the parity is similar. So this data we want to transmit is 7-bit. So for even parity, we have to make sure the total 8-bit data has an even number of 1. Have an even number of 1. So for the first value, for example, A, how many ones do we have? 3. Is 3 even or odd? Odd. So to make the 8-bit value even number of 1, the additional bit we add should be a 1 or 0. 1. That's why here we should give it a 1. So we know that we are using even parity. So we know that the data we are transmitting is this data. Then we have to work out what is the extra bits value. So for this one, we add 1. Then there will be a total of 4 ones in this data. So that's an even number. So that means this is the data we are going to transmit. On the receiver side, when people get this data, it will also look at how many so how many ones it is included in the data. If they say, oh, it's even number, it's very likely this data is not corrupted. So it's a valid data. It's very likely, but it's not 100% guaranteed. Okay, so second question, second example, 11111000. So the 7-bit, how many ones do we have here? 4. 4 is an even number already. So we have an even number of ones in the 7-bit. So what is the value of the extra bit we are going to add? 0, 0. So this is how we form the pattern for even parity. So on the receiver side, they will check what is a even number of ones. If that's correct, then the receiver side would assume this is a good data. However, when the next question is related to the so unguaranteed situation. So when sending a data of 11001110, so the parity bit is 0, and the data is corrupted during transmission and received as 1010110. So the transmitter, so as a transmitter end, we have this data. So we are using even bits. That's why we add the 0 bit there. This still even number of ones. On the receiver part, what's received is this data is obviously corrupted. It's changed this original value. It's not the correct data. However, the receiver won't know. It will. They will just calculate the number of 1 here. Oh, there's still an even number of ones. So they will assume this is a valid data, but it's not. So this is the limitation of the parity checking. So this algorithm itself is limited. For adding, so adding even number of bit, if they flipped value, we won't be able to detect the corruption of the data. So this is that's why parity checking, this algorithm is very limited. It's very fundamental. It's not fancy. You have to come up with a better algorithm if you really want to make sure that the data is valid. So we have a lot of algorithm already for that in software. For checking it, but in hardware, this is it requires a very small amount of hardware resource to do. Yes, question?
It's just like even bits.
Even bit can be, yes, odd bit can be, so odd number of bit. If odd number of bit change the value, then that can be detected. If even number of bit flipped, then it can't be detected. For example, one bit change the value, we can detect it. If two bits both change the value, any of these bit, including the parity bit, if two of them both flip 0 to 1 or 1 to 0, then we won't be able to detect it because the total number of ones will still be even here.
Oh, what if we have now 6 ones? So let's say we're still even, but then now we have more ones. Would you detect that?
No, it won't. It won't detect it. There is no extra circuit there for us to know how many ones are sent. We only know whether it's an even number or odd number. So we only have the facility to, in this algorithm, to count the number of ones to say whether it's even or odd. So there is no extra circuit for this. Okay, so very good question. Write down the HDL code for generating the parity bit. So let's have a look. The code. This is a multiplex code, 821128 code. We use with select to do, this is also with select. And so both direction, we use with select to define it. And here we got the HDL code for the parity bit checking. So the yellow and the green can do the same thing. So as we mentioned, for generate this statement in VHDL is nothing like for loop in C. Okay, so for loop is a sequential loop. For I equals 1 to n, it will run from 1, and the next loop it will be 2, and then it will run up to n. It will run n times sequentially. So see, first second you run for I equals to 1. The next second you run for I equals to 2. That is what we call sequential. In HDL, when we use for generate, it will generate this for I in 2 to 7. That means we have 6 bits there. It will generate 6 lines of code, and they will be running in parallel. That means they will be mapped on the FPGA in a flattened manner, flattened architecture. So with the for loop in our C coding, in our microcontroller or on the computer, it will run sequentially. It is the same microcontroller to run that function n times, right? So it's not like a 6 microcontroller to run this 6. Here we will get the XOR at the same time. So with VHDL, we have 6 XOR mapped on FPGA to run this in parallel. So this is the very important difference between these two.